Hello everyone and welcome to today's graph reading group.
Where we have a paper on pre-training with denoising 3D structures of molecules. Let's go.
So hi everyone, my name is Shah, and yeah, I'll be presenting this work on pre-training by denoising for molecular property prediction. Now, this work was done in collaboration with a bunch of people over here, most of whom are at DeepMind. And yeah, we'll also be presenting this work at iClear in a couple of weeks. So if anyone's interested in meeting in person and chatting, then yeah, in a couple of weeks, if you're in iClear, definitely hit me up. Okay, so the TLDR of this presentation, this paper, is as follows. And so if you were to leave the chat, the presentation right now, this is the thing you should take away with you, which is that if you're training a model on 3D structures, which is 3D coordinates of a molecule, as in the atomic coordinates, goes into your model, and you predict something, then you should consider pre-training it via denoising. And so this presentation is about exactly how we did the denoising, why you would want to do the denoising, and then experimental results around that. So basically, what's shown in this figure is just kind of a schematic. Denoising is your upstream task, and then you have a bunch of different downstream tasks. For example, prediction of different kind of regression properties. And then on the right-hand side, this is just sort of an example of a plot where this pre-training allows us to improve upon the state of the art in QM9. Okay. So the way my talk is going to be structured is sort of 4 sections. The first is about denoising. I'll discuss kind of exactly how we denoise, what does denoising mean, and then discuss a bit of like motivation around why we should do that, as well as theoretically motivating why this is a useful thing to do. Then I'll talk a bit about some molecular data sets and tasks that our experiments focus on. I'll go over the experimental results. And then finally, at the end, I'll highlight some avenues for future work that could be quite interesting to try out. Okay, so this in the beginning of the presentation, I'm just going to kind of talk about like what the task is and how we do that. For some people, especially people who've worked with GNNs for molecular property prediction kind of problems, this might not be super new to you, but if you're not, hopefully everyone's kind of on the same page. So the overall task that we're interested in over here is take a molecule's 3D atomic coordinates and atom types and maybe more information. So that's just depicted in this way over here. You feed that into a neural network, such as a graph neural network, and out comes a single number, a scalar, such as, for example, I'll say energy many times, but it could be something else. But for instance, the energy of the system is what you want to predict. We focus like throughout the work on tasks where you feed in a 3D structure rather than a 2D structure. So lots of different papers work on models which are giving, for example, smile strings, 2D kind of representations of the molecule. And also, like towards the end, I'll discuss a slightly different task where instead of an energy, we're predicting maybe like per node labels, such as, for example, forces on individual atoms. Okay, and then given a 3D molecule, such as, for example, a water molecule shown over here, the raw data in this case is, essentially a point cloud. You have 3 points, in this case, each corresponding to one atom, and then you have the coordinate of the atom as well as its atomic number. So that's just the, whether it's oxygen, hydrogen, and so on. And then we can represent this as a graph. This graph representation shown over here is specific to one of the architectures that we played with, but it's not in any way specific to the denoising task that I'll talk about. So here, for example, the node features are basically embeddings of the atom types, and then the edges are basically featureizations of the interatomic displacement vectors. Okay, and so bonds are going to be shown in some of these figures kind of mainly for illustrative purposes, because we're treating edges in the graph representation very much like other works where there's like a connectivity threshold, and if 2 atoms are sufficiently close, there's an edge connecting the 2, and otherwise not. So that's one thing to keep in mind. Okay, so pre-training by denoising. What is the high-level idea over here? The idea is you have 2 stages of training, just like people have in the pre-training fine-tuning kind of paradigm. In stage A, we assume that you have access to a data set A, which just contains lots of structures. So A is an unlabeled data set, doesn't necessarily need to have labels for the structures. You just have 3D structures in it. And we're going to do pre-training on it by denoising these structures, which simply means that we add IID noise to all the atom's coordinates. So that's a noisy, perturbed version of the structure. It's fed into the network, it goes through the encoder, message passing, and then kind of a decoder. And the decoder at the end outputs for each node a prediction of the noise that was added to the input. Okay, so this is a node level regression task where you're predicting the noise. And then, we use kind of a denoising loss and train this whole thing. Once that's done, you take your graph network and you basically retain the encoder and message passing units, but replace the decoder with a global decoder. And now you fine tune the network on, for example, feeding in a structure and predicting a scalar energy, for example. So this is kind of similar to how, you might pre-train a network on ImageNet and then replace the final layer, which outputs, for example, a 1,000-dimensional vector with like a 10-dimensional vector if you're fine-tuning on something like CFAR10. So that's kind of the, analogous to that. And then a simple, quick note on the architecture we use over here. It's called a graph network simulator, which has been used for problems in modeling physical systems before. And this is about 10 layers in the network, like the default configuration has about 10 layers repeated in blocks of 3. So that's kind of, it's a pretty generic message passing GNN. So it retains both node and edge features, and it does message passing to update them. Okay. So now that I've talked about sort of denoising, I want to give a bit of background on like why we ended up doing this, kind of the story of like how this research project came to exist. So the background here is there is a method called noisy nodes, which maybe some people might have heard of, where the main contribution of this work of noisy nodes by Goodwin et al., it showed that if you are training a network on molecular property prediction, then you can augment the training loss with a denoising objective. And that shows that you can get an improvement in the performance. So here they showed, I think Hannah says maybe a question.
Yeah, and right, this is when having the 3D atomic coordinates as additional input.
Yeah, exactly. Yeah. So this as well as focusing on the same kind of class of problems where your 3D structure is in the input. You don't have just, for example, a 2D structure. Yeah. Okay. And so what they showed in this work was pretty good results in QM9 and Open Catalyst 2020. And they also showed that having this objective allows you to scale the size of your network up quite a lot. So they trained models up to 100 layers and show that you get performance even when you go from 50 to like 100 layers. And typically in GNNs, it's been a little bit hard for people to scale them up for various reasons. So this paper basically, they proposed 2 explanations for why this idea of noisy nodes and auxiliary loss of denoising, why this works. One of the things they said is that perhaps denoising is improving representation learning. So by performing denoising on the structure, you're learning something about the distribution of molecular structures, and perhaps that's useful for the actual task you care about. That was one thing. And then the other thing they saw empirically is that there was less oversmoothing happening in the networks when they were trained with this auxiliary loss. So by oversmoothing, what I mean is it's been observed that GNNs, when you have multiple message passing layers, by, for example, the last layer, the node features are going to be quite similar across different nodes. And so, and this can sometimes affect the kind of expressivity of the network. And basically what they saw is that there was less oversmoothing empirically observed in the networks trained with noisy nodes. So these were kind of two explanations, and that's kind of our starting point. We wanted to sort of explore this more to figure out which one it was and see whether we can use that understanding to improve the models. Okay. So to recap, noisy nodes is using a multitask training objective, the multitasks being denoising and energy prediction, 2 separate things. But what they really care about is energy prediction. That's the kind of task of interest. So we had a few questions to begin with. Question number 1 was, can we split denoising and energy prediction into 2 different stages? Do we have to do them separately or not? So can we, for example, first denoise, in a pre-training sense, and then learn energy prediction in terms of fine-tuning, and still retain the benefits of having this denoising loss there? That was question number 1. And question number 2 was, if this works, can we denoise on a different data set, let's say a larger data set where we don't have labels, denoise on that, and then do fine-tuning for energy prediction on a different data set B. So here, there's also a question of like, is there transfer between denoising on dataset A, which might be different from energy prediction training on dataset B? And then lastly, like there's this one main question: why even should we denoise? Like, what's special about denoising? In the denoising is kind of used a lot for diffusion models, for generative modeling. What's going on over here? Like, why are molecular structures being denoised even like helpful for learning anything? Okay, and so suppose that pre-training about denoising works. What are the benefits of that? One thing is denoising is a self-supervised task, which means that we need only structures, not labels. So we can use it on data sets like that. Another thing is, when we wrote this paper, at least, and I think to some extent still now, methods for pre-training 3D models didn't exist. For example, if you look at QM9, some of the best models on that, they would usually be coming from new architectures are improving kind of the state-of-the-art performance over there. So that was one thing, to come up with a pre-training method that actually that helps a lot in practice. I think there's a question, Dominique.
Hey, yes, I have a question. So you talk a lot about denoising and adding noise, but you never explained like what kind of noise you add to what kind of conformations. And I was wondering if this would be coming in the next slides, or like if I should ask my questions now.
Yeah, I'll get into that a little bit more about the noise. And,
Okay.
yeah, definitely a valid, good question to ask. Yeah, I'll get to that shortly.
I'll let you go to that.
Cool. Yeah. So, and then last thing to say is that, denoising is something that you can potentially use. It can be a quite scalable objective in the sense that you can, combine data sets of data sets and denoise on them. And, with the aim of learning high quality, like representations for molecules. Okay. So now let's get to the, I think the question Dominique asked as well, which is method, kind of, explaining the method over here and why we would want to do that. Okay. So first off, I'll say before I guess going on to this slide, the denoising objective is very simple in the sense that we take a molecular structure. So that could be kind of a low energy or locally energy minimizing conformation. And the way we add noise to it is we take IID Gaussian noise of a certain amount of variance, and we add that IID to every atom in the molecular structure. And for the moment, you can think of the noise level, as in how much you perturb the structure, as a tunable hyperparameter. So you can just think of this something that you'll tune with cross-validation along with all other hyperparameters. So that's basically what we add, and then we ask the model to predict this noise. So that's really all that's happening in the denoising side of things. So let's kind of like maybe write this down a little bit. So I'm going to, for a moment, zoom out and tell you about denoising score matching, where kind of diffusion models came out, and sort of explain what the link between that is and the denoising that we were doing in the molecular world. So for a moment, just clear your minds and think about score matching, which works as follows. Score matching is basically this idea that if you have a distribution Q from which you have a bunch of samples, x1 to xn, you're interested in learning the score function. And the reason you want to do that is because there are ways that you can use the score function to sample from that distribution. So that's kind of your end goal, let's say. And score matching, what it ends up becoming is basically minimizing the following objective, which is you have a network phi theta, which is learning the score function of the data distribution, which is Q. And the main kind of in the kind of generative image generation models and diffusion models and stuff, one of the main things over here is that, okay, if you want to learn the score of a distribution, there are two difficulties. One is this expectation is something you can compute in closed form, so people usually would replace this with a Monte Carlo estimate. And the second thing is that the score function, the true score function, is unknown. So people have ways to basically work around this. And one of the main ways that they work around this is basically you replace the true distributions score, so grad log Q, with grad log of an approximation of that distribution. In this case being the noised version. So let's say Q is your true distribution, Q0 is your empirical data distribution. You can define the noising distribution and the noised data distribution. All these are basically is, the noising distribution basically is a conditional distribution that says, given an example x tilde is basically adding noise to x. So it's just a Gaussian centered at x. And then the noise data distribution is a marginal distribution of the noising distribution. So sampling from the noise data distribution just means you pick a random data point and you add a certain amount of noise to it. Okay, so that's what it is. And the main reason you do all of this is because replacing Q with Q sigma, i.e. the noised version, makes this objective function more tractable. And it turns it into a denoising loss, basically. So this was shown by Vincent in 2011. And it's basically it at least kicked off the initial kind of score-based generative modeling work. So that's kind of what happened there. So this is just some background. And I'll tell you how this relates basically to our setting. So now think of X as a vector of coordinates. So let's say we fix the molecular composition. And so the entire way a conformation and structure is defined is using a 3 n-dimensional vector X. So this X is basically just the coordinates of each of the atoms in the molecule. Then one thing we know is that equilibrium structures are local minimizers of the energy. So E of X is your energy, and local minimizers of that are going to be these energy minimizing structures. And then the forces are given by negative grad E of X. So this is something we just know. The energy function, take the derivative, and the negative of that are the forces. So the crux of the denoising work, basically, I mean, our speculation, one of the speculations here is that suppose we could learn negative grad E of X, then we think that that might be a useful thing. That might be a useful way to build good quality representations for downstream tasks. So this is to begin with just a speculation that we want to empirically check out. And so let's set for a moment, let's set our goal to be learn negative grad E of X using only the equilibrium structures. So remember that we only have access to a bunch of conformations, a bunch of molecules which are minimizers of the energy. So we don't know anything about negative grad E of X. At least we know that the negative grad E of X of these local minimizers is 0, but we want to learn the function negative grad E of X using just access to the equilibrium structures. So let's say we want to do that. Okay. Now going a bit more into detail on this side of things. If you define P physical to be the distribution which is proportional to the exponential of minus E of X, this distribution, the Boltzmann distribution, then the score function of this distribution, which is grad log P physical, is exactly equal to negative grad E of X, which is the forces. So learning the forces, which is negative grad E of X, is the same as learning the score function of the Boltzmann distribution. So you can phrase learning the forces as minimizing this objective function. So this is now we're in the score matching world. So we take the Boltzmann distribution, try to learn the score, and if we do that, that's a way of learning the forces. But once again, as before, just like the score-based generative modeling world, we don't have access to the score function, this grad log P physical, and we only have access to equilibrium structures. So before they had access to, for example, images, we have access to equilibrium structures, and we don't know the score function. So
one
how would we
interruption?
Yeah.
What exactly do you mean with equilibrium structures? Are these just some structures and modes of the Boltzmann distribution?
Yeah, exactly.
Why do we call them equilibrium structure?
You can call
Or
them,
like,
yeah.
No.
Yeah, I'm so in this case, I guess equilibrium structures is just literally defining that to be locations which are modes of the Boltzmann distribution.
Okay.
Yeah. So now let's think about how we can basically try to learn this learn the score of the Boltzmann distribution using equilibrium structures. So suppose this is,
you're not really learning the score of the Boltzmann distribution and not really learning the you don't have samples from the Boltzmann distribution, you only have your modes. So you're not really learning the forces, and you're not really learning a force field, and you're not really learning the score of the Boltzmann distribution, but of this delta distribution, or of the sum of these delta distributions, if you want to call it that, where the that is then renormalized, where the modes are weighted accordingly. Or do you even weight the modes accordingly, or do you just take them all to have the same weight?
Yeah, so you're exactly right that you don't actually have samples from the Boltzmann distribution. That would mean, having examples which aren't, energy minimizers, or in other words, modes of the distribution. But so suppose you have, this is your distribution, and all you know about this distribution is where its modes are, right? So basically all you know about it is these things, the locations of the modes. The question is, what can you do with this very little information about the Boltzmann distribution, right? One of the simplest things you can do is you can basically place a mixture of Gaussians at each of those modes, right? And this is going to do the kind of the minimal possible thing you can do with this little bit of information, which is that this blue distribution at least approximates the red distribution, in that wherever the red distribution has a mode, your mixture of Gaussian will have a mode approximately in the same place. So this is kind of the minimal thing you can do.
So you're not scaling the Gaussians according to the Boltzmann weights?
No, in this case, you're doing nothing other than literally placing, a Gaussian. You're placing one Gaussian in your mixture at each of the modes.
Yeah. And did you try that during pre-training to like sample the more common modes more during training, or like
So in this case, no, so we didn't try doing that. And I think that's actually, so yeah, I was going to talk about this towards the end, where I think this is one thing where we can do better. As in basically this approximation that I'm talking about right now is kind of the most minimal thing you can do. And, we've noticed, as I'll talk later, like in the experiments, we already saw that this is giving you, interesting kind of results on downstream tasks.
and
so
I
now
mean,
it makes sense to, see if you can, do better by having a better approximation of the Boltzmann distribution.
also in the end, it's just like a nice story, right? Like a nice interpretation that maybe gives some motivation for doing this pre-training, but in the end, it is what like the pre-training just either helps or doesn't, and we'll see.
Yeah, exactly. Yeah. So yeah, in this case, I mean, in some sense, if you take a pragmatic approach, pragmatically, what you see is that doing this pre-training by denoising is going to improve your results on multiple downstream tasks, which I'll talk about later, right? So this was basically, a way to understand what is denoising actually doing, right? How can we interpret the denoising objective in the world of molecular structures? What can that actually be interpreted as, right? And of course, the hope is, once you have this interpretation, you can say, okay, fine, I can do better if I know something about the curvature, for example, of each of the modes, right? And then I can essentially, weight the different Gaussians or vary their width, essentially, to be able to get a better approximation of the Boltzmann distribution. So here, the fact that we use the same noise for every molecule means that, the width of each of the Gaussians is kind of the same across the entire thing, right? So that's like one thing I think it's definitely a good idea to try, is basically, should we be varying the noise level in accordance with the thickness of the Boltzmann distribution at each of the different modes, and see whether that improves anything. Okay, let me move on then.
Yeah, but in general, like in most data sets, you won't even have the thickness, no?
Yeah.
Because it's way too expensive to compute unless you use molecular dynamics. Then you can have the modes, but molecular dynamics will use force fields with very approximate values, and then your pre-training will also learn on some approximate values. So I'd say this is not a bad way of doing things. And in the end, maybe even considering the energy is not such a problem, because when you learn the denoising, I mean, you'll never have a noise. Wait, where's the... Yeah, I don't have my annotation option right now. Maybe, but you will never have a noise that will get you from one mode to the other mode. You will usually stick with noises that are small, and just because of that, like I don't think it's because you're learning the energy as a second function. You're learning one function as the noise around the state, and the other function as like the energy. So in the end, like you don't necessarily learn how both of them relate to each other,
Yeah.
but explicitly, but implicitly you might do.
Yeah, I think like yeah, as you were saying, I mean, like in a lot of data sets, it won't come like, hey, here's a mode and here's kind of the curvature of the energy function of the Boltzmann distribution around that mode, right? And so that's why, yeah, you might not necessarily have that information. Now, I've also learned that there's things like I don't know exactly whether that would give us what we want, but things like I think like B factors and stuff tell you something about how much different atoms can wiggle in certain areas, which might give you some hint as to like if something can, for example, wiggle quite a lot, that might, one way of interpreting that is that the energy is actually not too affected by that thing wiggling, right? So maybe that gives you some hint as to how thick the energy function is and potentially how much noise you should add there.
Yeah, that's definitely can be useful, like when predicting the noise, also predicting like a sort of tolerance or like the B factor related to that noise. So it makes sense.
Yeah. And as another thing you mentioned that's quite interesting is that you said that, yeah, could we ever add so much noise that one conformation goes to another conformation, right? And I think like what's interesting there is that suppose your noise level is so high that when you add noise to the molecule, the network basically has no way of being able to predict what the original conformation was, right? Then one thing you'd see is basically the denoising training loss will essentially struggle to even go down, right? Because you've essentially destroyed all the signal that might be in the input for predicting the noise. So one way to see whether your noise level is so high that you're jumping between conformations is if the denoising training loss literally is struggling to go down. Okay. Yeah, so I'll move on now. So basically, the long story short of what I said right now is that if you essentially approximate this red thing with the blue thing, then you're essentially able to apply the earlier result of Vincent in 2011 and realize that learning the score function of the Boltzmann distribution is the same as denoising. So the kind of one-line summary of everything I've talked about right now is that if you want to learn the forces, then learning the forces can be phrased as score matching with the Boltzmann distribution. And in order to do the score matching with the Boltzmann distribution, you apply this one approximation. And if you apply this approximation, then you end up with a denoising objective. So that's kind of the link for there. Okay, so this, I hope, like gives somewhat an idea of at least like an interpretation in the world of molecules. What are you doing if you're actually denoising structures? Okay, and finally, I want to like highlight a few differences between denoising for learning forces, as I just described right now, versus denoising for generative modeling as people use in, for example, in diffusion models. So one difference is that the data that you have in this world of molecules is local maxima of the true distribution, i.e. modes of the distribution. Whereas, when you're doing denoising for generative modeling, you have actual samples from the entire distribution. So that's one difference. Another thing is that because you have actual samples, in generative modeling, you want as small noise as possible, which is what's discussed in the paper by Song and Herman, that you want a small noise value, but you need to kind of take a multi-scale denoising in order to be able to approximate the score function away from the data distribution, right? That's one thing. But in our case, we actually want a non-zero amount of noise. The reason being because we only have examples at each mode, so we need some sort of thickness around each mode to be able to capture the fact that the Boltzmann distribution is not just a delta there, but it might have a little bit of thickness around there. And lastly, our goal is not to sample new conformations. Our goal is to learn the forces, because we speculate that that's going to be useful for downstream tasks. So those are kind of the differences between the two. Now I'll go over to the experiments. For the upstream, so one question over here is, okay, let's say you want to fine tune, as in your downstream task of interest is QM9. What should your pre-training data set be? So the main data set we work with in this paper is PCQ M4M V2. I'm just going to call that PCQ, which is a bunch of data set, a bunch of molecular structures, 3D structures, over 3 million of those at equilibrium, calculated using DFT. So comparing that with QM9, PCQ has over 3 million examples. QM9 has like around 130,000. On average, PCQ has bigger molecules. They have 31 instead of 19 atoms. You have more diversity in terms of the species, but you have much fewer labels. So you have 12 labels per target, 12 targets per molecule with QM9, whereas PCQ you just have one, I think the homolumo gap. So the point is like, this was the data set we thought is a good data set essentially to try this idea of denoising on it, right? Because we have lots of these examples. Okay, and then comparing a bit like how similar the distributions of PCQ and QM9 are, here's a plot where the x-axis is kind of a molecular composition, so like a stoichiometry. And then the y-axis shows the number of times that specific composition appears in each of the data sets. And this graph is showing only for the examples that appear in QM9. And as you can see, there's like a good amount of coverage between PCQ and QM9. So PCQ covers QM9 quite well, but then there's a lot of stuff in PCQ that's also not in QM9. And one thing to note is that even if the molecular compositions are the same, that doesn't necessarily mean the geometries are the same, right? So in that sense, there isn't a worry of data leakage. And the biggest thing that ensures there isn't data leakage is the fact that pre-training with denoising doesn't even have labels, as in like we never use the actual energy, homolumo, whatever it might be. We don't use those labels in just the structures. Okay, and here's just a few visualizations of what these examples look like. PCQ, generally bigger molecules, more diversity than QM9. Okay, so here are results on QM9, where you have a number of baseline architectures from the literature. And then we have a few examples over here, which are basically the GNS architecture I mentioned earlier, the graph network simulator, and then the pre-trained version. And the takeaway from here is that, well, first off, noisy nodes helps a lot, which was the finding of the previous work. And then the main finding of our work is that adding pre-training on top of that improves performance on nearly every task over here, and gives you state-of-the-art results compared to models in the literature on 10 out of 12 tasks in this case. So that's one thing. So going back to one of the questions I asked earlier, can you split denoising and energy prediction into two tasks, unlike noisy nodes? The answer to that is yes. And you can also transfer. So you can pre-train on PCQ and then fine-tune on QM9, and this is what comes out of that. Okay,
so here we pre-trained on PCQM4M and then fine-tune on, or then we make our predictions with the 3D information of QM9.
Yeah.
Okay.
Yeah. So you basically pre-train the model on PCQ with denoising. You just take the weights and then initialize with those weights and just train as usual on QM9.
Mm-hmm.
Yeah. So that's the difference that comes up over here. And in each case, we found that applying noisy nodes, that is keeping the denoising objective on QM9, was generally never hurting performance. So that's kind of like on in all of these cases. Okay.
Yeah,
so
thanks.
that's that.
So it's yeah, I don't think it's surprising like to see that there's some performance improvement like by pre-training on PCQM, like especially at the conformation level. Of course, if you train only on like the homolumo gap and then you try to generalize everywhere, it won't work really. But as you mentioned, like learning on the noise allows you to learn like really the forces and the interactions between the atoms. But hey, perhaps I missed that part, but like you never explained what kind of noise you added on the atoms. But I had to log off for 2 minutes, like so maybe I missed it. But like, do you just move the atom position in any random direction? So each atom moves from a Gaussian noise to another position. Like, how do you apply it?
Exactly. Yeah. So let's say you have like 10 atoms. You basically sample a 3-dimensional Gaussian vector 10 times, IID, and you basically add it to each vector. Each atom. So you're independently perturbing each atom by a bit of Gaussian noise. And the noise level we use, we tuned that, and I think in this case around 0.04 was roughly a standard deviation. All these hyperparameters are in the paper. So yeah, we set a certain amount of noise that's tuned.
Okay. Yeah. Have you observed, like, visually looked at molecules before and after the noising and seeing how much impact it had in the noise that you selected?
Yeah. So we were we took a few examples, this one in QM9, not PCQ, and just kind of add a bit of noise. You can basically, yeah, you can kind of like see, you know, like if you add a very little amount of noise, basically nothing's going to change, and you know, there's not going to be anything happening. Whereas if you add a lot of noise, you're basically going to like destroy the molecule altogether.
Yeah.
And generally, if you look at performance as well as a function of the noise structure, there's kind of a, you know, sweet spot. Too much noise and too little noise are both going to be suboptimal. Yeah, there's like a sweet spot. Yeah.
Okay, cool. And another thing, like, is like the type of noise that you add is just like moving atoms at different positions. But like one of the work I really like a lot in the diffusion model for generative 3D structure is torsion diffusion, which adds the noise specifically on the torsion angles, because any other part of the molecule like cannot doesn't change that much. Like the bond angles and the bond length don't change that much. Whether here like the noise that you add won't necessarily affect the torsion angle a lot, but it will affect everything else a lot. So like, yeah, I think maybe a good thing for future work would be exploring how different type of noise, like separating the types of noise by like, if I noise only the bond length, now let me noise only the angles, now let me noise only the torsion angle, now let me noise just random position, and seeing the impact of all these different noising in the pre-training. I think that would be very valuable, because just a random Gaussian noise is not something like, it's not something that necessarily makes sense.
You can do, right? Yeah.
Yeah. It's the simplest thing you can do. Yeah.
Yeah, like for example, you know, if you take a torsional view of molecules, yes, 100%, you can like basically do the exact same denoising idea and do it on you know, the torsion angles and for example bond lengths and so on. Yeah, I agree with you. And I think like you know, if you're denoising, for example, bond lengths, you might want them to be positive, right? And then a Gaussian distribution might not necessarily work, right? So I think another angle over here is like, is Gaussian distribution the best one, right? Maybe you should be adding, you know, kind of maybe heavy-tailed kind of noise. So yeah, I think like that, as well as like whether there should be different amounts of like noise, sorry, the variance of the noise should also maybe vary between molecules, between atom types. Yeah, there's a lot of stuff that you can try over there that we haven't even gotten to trying yet. Yeah. So I think, I mean, like, this is sort of like, I really think it's like the V1 version of this idea. And yeah, there's quite a few things that you can play around with that we don't even know the performance of yet.
Yeah, definitely. Because especially like when you mentioned that your model is kind of an approximation of learning the equilibrium around a local minimum, a local energy minima. Well, around that local energy minima, what will change the most is torsion angles and not like all the other stuff. So it makes like, yeah, I think maybe a future work would like explore how you can couple all these, perhaps with the different variants for each of the type of noise. But yeah, I think as a first step, like it's really nice the results that you get now.
Yeah, and I think like you know, if you have architectures that take the bond length and torsion angles as input, for example, for QM9, and then predict the labels, you know, those kind of architectures, yeah, you should definitely like a denoising that happens on the bond length and torsion angle world. That would make quite a good sense. Yeah. Okay, I'll move on from here to another set of experiments. So we tried this other data set, this DSHA-15K data set, which is a bunch of dimer geometries. So that's like two molecules having non-covalent interactions. And here the task is similar, you know, take the geometry and then predict the interaction energy. And in this case, unlike QM9, these molecules are, the geometries, sorry, the labels are calculated using CCSCT. So they're like much more expensive labels than DFT on average. And so here we again, you know, similar to before, we find that, yeah, denoising on PCQ and then fine tuning on DES15K gives good performance. And in this case, we actually have even less overlap between PCQ and DSHA-15K. So there is a kind of more of a distributional shift between the upstream and downstream data sets. And then moving on to OpenCatalyst 2020, this is kind of the data set that's even more different from PCQ, in the sense that here you have, you know, catalysis relaxations happening. So, you know, not like small organic molecules like we had in the earlier data sets. And you can kind of see that over here. The atomic types that appear in OpenCatalyst are quite different from PCQ. And here the task, there are multiple tasks, but one of them that we played with is given the initial geometry, so that's like a high energy geometry, predict the energy of the relaxed geometry. So that's kind of the task over here. So here we found actually that pre-training with PCQ. So first off, doing no denoising, no noisy nodes, no pre-training gives significantly worse performance. That's a red curve over here. So this is the validation energy MAE. So you need to denoise in some way, either noisy nodes or some sort of pre-training in order to be able to improve the performance. And here we tried two things. One was PCQ itself, but PCQ, as I said, is quite different from OpenCatalyst 2020. So we found basically that it wouldn't necessarily give the best performance. But then we tried another thing, which is just pre-train on OpenCatalyst 2020 itself. So now this is kind of suboptimal in the sense that you don't have extra new data in some sense. So it's harder to maybe learn something that's outside the downstream data set. But we found that if you do that, then there's very quick convergence. Initially, the model converges really fast, and then sort of like levels out, converges around the same point as just using noisy nodes.
But that is after pre-training for a long time, right?
Exactly. Yeah, definitely. So here, the noisy nodes one is trained from scratch, which means that you haven't put any compute cost beforehand. So here you've pre-trained and then fine-tuned the model. Yeah. So in this case, I think an open question really is like, what is a good pre-training data set that will actually improve upon the state of the art? And yeah, here I think we can match it and converge, but yeah, not necessarily get better performance. Okay, and then so a bit of like analysis here was also the representations you learn from denoising, are they good? And so to ask this, to kind of get a answer in this direction, what we did is we pre-trained the network and then just froze all the weights except the decoder. So the way you can think of this is you pre-train the network, and then on the downstream task, you take the molecules and construct their pre-trained representations, and then fine-tune a decoder on top of that. And we compared that with using random features. Basically, just don't.
Where does full model training fall here?
That's down over here, the green curve.
No,
this
that's
is on
full
QM9.
model training with pre-training.
Full model training, as in you pre-train the full model, and then during fine-tuning, you also like fine-tune all the weights.
Yes, that is the green curve. But is there also a curve where where would the curve fall if you do not pre-train, if you do just full model training?
I see, full model training from scratch, no pre-training, right? So that's not over here, but it'll fall around, for this architecture GNS, it'll fall around 30. So between the, so around here.
So you remember that the final MAE was 30 for that.
Final MAE was 30, yeah. So this is basically the GNS architecture without noisy nodes, yeah. I think it was like 28, 29, 30, something in that ballpark for Homo, at least on this task, yeah. Yeah. So here, basically, I mean, it's no surprise that that's going to do better than, pre-trained features, because here all we're training is a deep set kind of architecture, just a decoder. So this is a quite small chunk of the entire network that's being trained on the final representations. And obviously, like full model fine-tuning is, that's the best in this case. A thing that we want to see is whether you can, get so high quality pre-trained representations that basically, all you need is those pre-trained embeddings of a molecule, and you can essentially match the performance of networks trained from scratch. That I think would be a vision, but there's still, a performance gap over here to close. But I think if that works, I think that can be quite high impact, because people don't have to train sort of giant, 100-layer GNNs from scratch. You basically just much like the language world, you embed your molecules and then just quickly train a smaller network on top of them. Okay, and then lastly, a few data scaling laws kind of curves. We suspected that pre-training might be good for small data, and which is what you see again on QM9. We saw that if you take, for example, only 5,000 examples from QM9, then the pre-trained model is going to do almost its loss is basically like almost half the loss of a model trained without trained from scratch, basically, and no denoising. So generally, smaller data, we find that pre-training is more useful, which kind of goes with the intuition. And also, like, if you have more pre-training data, that also helps. So on the x-axis here, we're varying the amount of PCQ data we use, and generally we find that for at least for GNS, like going even from 1 million to 3 million examples, there is an improvement that you're getting. So yeah, I think, and another interesting thing is, like, if you look at the denoising losses, we found that you can keep scaling up the architecture, and that loss is going to keep going down. And I don't think we necessarily hit like a saturation point. because denoising is something that it's kind of hard to overfit to, because every time you sample noise, it's a new amount of noise, right? So in some sense, you don't just have 3 million examples, but 3 million examples times the number of different noise vectors that you saw for them. So yeah, I think like high capacity architectures for really like pushing this is yeah, something I think that could be a good direction. And then lastly, model scaling with OpenCatalyst 2020, which is a kind of a bigger data set. We played around with scaling the model up to a 1 billion parameter model, and generally found that pre-training helps there as well. Here we found that you can take a 130 million parameter model, which is trained from scratch, and that's going to be outperformed by a model that's half the size but pre-trained. But generally, the benefit of pre-training extends to even a 1.2 billion parameter model, and that's the largest one that we were able to train in this one. Yeah, question.
Yeah, just a very, very minor question, comment here. The y-axis, like, it would be nicer to have it in log scale to really look at the scaling law and the like where it would go, like at the infinite, yeah, where it would go, like if you continue increasing the parameters by doubling and doubling and doubling, or increasing the data by doubling. But I think these are very interesting, like curves that you have, like showing that bigger models and bigger data are super helpful. Now the question is like that remains is like, can we get the bigger models and bigger data to match what's happening in language and vision?
Yeah. So that's kind of part of the motivation and sort of the vision over here is that, yeah, can we replicate to some extent what people are doing with language models, where at the moment it seems like there isn't a saturation in sight in terms of scaling, right? But yeah, I think these ones, yeah, like if you take the last points and plot them on a log kind of plot, yeah, that will give some indication of whether there's a saturation, or maybe even if it's kind of like a power law that's matched quite well to get an indication. Yeah, I think with these sort of data sets, one thing is you can scale up the model, but the other thing is, can we scale up the data in tandem with that fast enough so that the models aren't just overfitting past a certain point, right? OpenCatalyst, I mean, that's a pretty big data set, so here you can really go to a 1 billion parameter model and it'll still be better than something that's smaller than it. But yeah, I'm not sure how such a thing would look on QM9, because QM9 you can overfit much more easily.
Yeah, definitely. QM9 is very small and has low diversity.
Yeah.
Yeah, like at some point, perhaps like using the machine learning models to sample more data, to then retrain the GNN model to then sample more data and such.
Yeah.
Like having a loop like that, where you take the advantage of past GNNs and like to generate more and more data. I think like that would be helpful in the future, but we're not there yet.
Yeah,
it'd be great to have some sort of active learning loop like that.
Yeah, and also like kind of the distillation benefits that come from generating more data and then feeding it back and training your model on it, right? Yeah, certainly. I think that's a good direction.
Yeah.
And then last thing, we also we briefly checked out whether you can improve force prediction. I talked a lot about denoising be similar to learning kind of the force landscape. And so we tried like force prediction with OpenCatalyst 2020, as well as force prediction on MD17. And we generally found that you see an improvement on the force side of things as well, which is what you would expect, because denoising in one way is force prediction. And we played with this architecture called Torch MDNet, this transformer-based architecture, which is a really nice architecture and not a huge one, so you can train it relatively fast. And basically we were able to find the same thing that on QM9 you can improve results, and like MD17 improve results by doing denoising pre-training on PCQ with it. Okay, cool. So just to conclude, what I've talked about, denoising is a powerful technique for representation learning. Our experiments show that, and we think that the reason denoising is working is because it's approximating and learning the physical force field, as in the force landscape around the structures. And we then found that Pre-training is beneficial across a bunch of tasks, CCSDT energies like DES 15K, QM9, Open Catalyst 2020. And it seems that pre-training might be especially impactful when you have little downstream data. So then you can, pre-train a model on something like PCQ. And if you have small amounts of data, that's where you might see the biggest benefit of pre-training. So those are the main conclusions. And then a few future work things. I mean, I think we touched upon lots of interesting future work things. I put down a few questions that I had here as well. One is, does a better denoiser also transfer better? So if your denoising performance is better, does that also mean your downstream, for example, QM9 performance is going to be better? That's one question. Another is, does denoising help other spatial problems? If you go to like point cloud classification where you might not have this whole force field sort of interpretation, can we apply denoising there and then improve point cloud classification? It's a completely different setup, but conceptually quite similar. Another thing is denoising by contrastive learning. Let's say you have two instances of a molecule, two structures. You give them both independent amounts of noise, and then you ask for their embeddings to be quite similar, but different from the embeddings of other molecules. So basically, contrastive learning where the augmentation, as it's done in images, is replaced with adding noise to the structure. And lastly, we talked about this quite a bit. Can we approximate the Boltzmann distribution better than what we did so far? So what we did is like the most basic thing you can do, and we can see good results across multiple data sets. Can we be smarter about the way we approximate the Boltzmann distribution? For example, using like B factors or some sort of sharpness of the energy function. And then, what kind of objectives does that give rise to? Okay, cool. I think that was it. Papers in archive at this link if you're interested, and we'll also be at iClear in 2 weeks. So if you'd like to chat, I'll be there in person. Just get in touch, and I'd be happy to chat. And thanks a lot to Hannes and Dominic for inviting me and arranging this. I think it's a great way to talk about the paper and see what people think and get ideas for future work.
And we thank you for the nice presentation and discussion. Yeah, I also think this is a nice way to get new ideas and have a few questions as well. And other people, feel free to put questions in the chat, raise your hands and so on. But what I wanted to ask about is maybe first a more general question about what do you think of pre-training with 3D data and then only fine-tuning on molecules where you don't have 3D data?
Yeah, I think you've done some interesting work on that side of things, right? So,
Yes.
So yeah, we focus exclusively on downstream tasks where you are giving the 3D information to the molecule, to the network. But there was actually some follow-up work of our work that was doing like this joint 2D, 3D kind of thing, where the 3D thing would be the denoising, very similar to what we've done. And then the 2D thing, I think they tried a few different approaches, like autoregressive kind of approaches. And I think they found, that if I understand and remember correctly, they did find that you can apply denoising in the pre-training world with 3D structures and then go to tasks where you don't have 3D information. And I think your work also has shown directions. So I think there is something to be learned from 3D structures, and whatever that is, it might not be limited to models that are then being fine-tuned on 3D structures as well. You can switch over.
Okay, but yeah, it sounds to me now like I don't know the paper that you just described. Do you know the title?
Let me actually. So this was, I think it was something like one transformer can learn 2D, 3D, something like that. Yeah, one transformer can understand both 2D and 3D data. So I sent this in the.
Thank you. Very nice.
Yeah. Is it the transformer M paper?
Yes, exactly.
Yeah, the transformer M.
Yeah.
Okay. Yeah. That's it's a good thing, but like the problem like with this data set, like the major problem I think with everything pre-trained on PCQM 3D structures is that there's only one conformation per molecule. So you're not going to learn everything about the molecule there. One thing like I'd love to see in the future is like, what if you have a 3D GNN that's pre-trained maybe the way that you pre-train it, like to understand like the forces and energies via denoising, and then you use some sort of distillation or teacher learning where you have another 2D GNN that tries to learn the distribution, all of the distribution related, all of the conformation related to one specific molecule. So that way, like the 2D GNN has all of the information about all the conformation and the distribution, the Boltzmann distribution. Like how to achieve that, it's still unclear, but it'd be great to have that in the future.
Yeah, I think if you generate a data set where you have like multiple conformations and lots of modes, and then sort of denoising on that. I wonder whether you might have to do like for each molecule you pre-train one thing, sort of one network, and that's kind of specific to that thing, and then that knows everything about that molecule's energy landscape.
Some sort of like the 3D Informatics paper that Hannes and I authored, but where the 3D GNN is pre-trained on denoising, and then the 2D GNN tries to learn like the 3D GNN that was pre-trained. So that'd be cool. But
get some kind of like latent 3D latent kind of hint about what the 3D landscape looks like. Definitely. Cool. Are there any questions on the chat that I should look at, or?
Nope, we answered some, we picked some out, but Levis would have a question. Unless he does not unmute, then there's no question.
Oh wait, sorry, was that for me? Yep. So thanks a lot for that talk. That was super interesting. One thing I was curious about, you've showed how this pre-training isn't as helpful if the molecules you're pre-training on are really different from the ones you eventually want energies for, right? For the Open Catalyst data set. So I think what could be interesting to look at is how good do those 3D confirmations need to be that you train on, that you denoise, right? Because otherwise you could very cheaply generate sort of approximations to equilibrium structures using a force field for the exact types of molecules that you're interested in to get energies. And then you pre-train on this, and it's all very cheap. And then you hopefully need a lower number of labeled data points to get a certain accuracy.
Yeah, that's a really good question. And we were also like thinking about this exact thing, like what does the quality of the geometries need to be, right? In order to like pre-train and still learn something useful. Yeah, so I think you're definitely right. Like you can take, for example, like RDKit or something and generate like lots of really, really cheap geometries that might not be like great, but they're very cheap and they're not like random. And then pre-train on a huge data set of those and see what happens. Ideally what you'd want is something like, this plot I showed earlier where you have the more pre-training data helps. In a way, you can think of the x-axis as the cost of generating the pre-training data set, right? And one way you can vary that cost is by changing the cost of generating each geometry, right, in the data set. Yeah, so like a plot like this where the x-axis is, the quality and cost of the geometries versus how well it helps. Yeah, I think that'd be really insightful to do.
Okay, cool. No, but very nice work. Thank you.
Thank you.
Yeah, in some sense, like one thing that you can do to look at the quality is like, instead of like having RDKit and then like semi-empirical methods and then DFT methods, which all take different time to compute, you can take like a data set like the PCQM or the Open Catalyst, and then use force field from RDKit to kind of adjust the conformation by doing one-step adjustment, two-steps adjustment, and such, so that you go from the perfect conformation from like the DFT methods to the imperfect conformation from the RDKit model, and you look like at the different data set, like the data set that is with RDKit force field minimized, the data set with DFT minimized, and a few data set in between, and look at the correlation between like the precision that you need, the precision related to the performance. I think that'd be super cool to do.
Yeah, I definitely agree. Yeah, the x-axis then literally becomes a number of steps you take and kind of like the cost, right, of generating the geometries.
Yeah, exactly.
Yeah, I 100% agree. Yeah, I think that's I'd be very curious if anyone does that. I'd be really curious, and if I get around to doing it, I'll let others know.
Yeah, definitely. And if you can get like something that's a very good pre-training from less accurate methods, then it's going to be really, really good, right?
Yeah,
But
and that's
in the end, I
scalable,
expect
right?
there's limitations. It's much more scalable. Yeah,
Yeah,
you can
exactly.
generate 1 billion molecules in a week, right? Another thing, like I wanted to mention, and it goes back a bit to my point about like the way that you add noise, is that you mentioned many times that the perturbation that you add, like learning the denoising, is similar to learning the forces, and the intuition here is a bit right, because like the forces is related to the gradient of the energy, and then you can say the gradient of the energy is related to the delta of the position. But
Exactly.
the thing is, it's a bit wrong because it's not, as I mentioned, like if you change the torsion versus if you change the angle versus if you change the bond length, there's like 3 different functions that that apply there. And right now it's like really linearizing all the system. Like you basically consider that any type noising an atom in any direction is really related to the gradient of is linearly related to the gradient of the energy. And that's not true, because in some directions the gradient of the energy is very small, and in other directions the gradient of the energy is very high. So this, like, yes, it's related because forces is gradient of energy, and gradient of energy is related to delta positions, but the relation is very nonlinear. Even under very small noise, the relation is nonlinear because
you can, like, for example, if you think about like doing gradient descent, that's kind of like taking little steps towards the minimum, right? And you can think of denoising as doing like literally one step towards that. But yeah, one step might not necessarily get to the minimum, and you kind of have to do more steps, right?
It's clear that pre-training with more data is a promising direction for many applications, and I really like this work with pre-training with this 3D structures and denoising. So if you want to see other cool works like this in the future and ask your own questions, join us in the Zoom call. All the information is in the description.